Hello, everyone. I presented to NANOG about 1 year ago, and after that presentation, I thought, will there be anything interesting happening in the next 1 year? Oh, yes. And boy, I was wrong. So the purpose of this session is to do a number of things. Go through what has been happening in the last 1 year, give you a little bit highlights, help you to understand these attack types and how to defend against those, and then try to look a little bit about new approaches to how we can deal with those threats and issues. So basically, I'll go through some trends and look at those different attack types, and then the need for increased visibility. First of all, there's a URL up there, so if you want to take a closer look, then you can download the URL. But basically what we're saying is the attack size, the max attack size, and in this case we're comparing the first half of 2017 to first half of 2018. The attack size has increased by 174%, which is a pretty nice number. So it went from 622 gigs to 1.72 terabits. And the average attack size has also increased 24%. But the frequency has gone down. This basically translates into that there are fewer attacks, but they're a lot harder hitting. And there are two reasons for that. Number one is that the attackers have realized that if you hit someone really hard, he is going to stay down. You don't need to launch a lot of attacks. If you just take him out with a big punch, then he will probably go down. And the reason why they're able to do that is that the attack toolkits, they are now readily available on the internet. And like, for example, I'll come back to it a little later on, is the time from a new attack type being launched on the internet, like the Memcached attack with 1.72 terabits, it took 5 days before an attack toolkit was available on GitHub. 5 days. And after those 5 days, it took about 2 or 3 extra days before that was included into the booter stressor services, where you can go and pay $5 to launch an attack against anyone. Then, which means it takes 1 to 2 weeks before something new comes out, and then anyone which has $5 in his pocket or on his Bitcoin attack account is able to use it to launch it against you. So that's how quickly things happen today. So if we take a look at some information about what has been happening here in North America, and this includes the US and Canada. Canada is the tiny little yellow thing at the bottom, sorry. Then in the first half of 2018, 734,000 attacks, inbound attacks, and the total volume 1.05 petabits. That's a lot of garbage traveling through the networks with no purpose other than to attack someone. And the average attack size was 1.43 gigs. And this is actually an increase from 1.2 up to 1.43. So the average attack size is increasing. And so there were 7 attacks greater than 300 gigs in North America, compared to 1 last year. So the attacks are becoming larger, harder hitting, and you have to be prepared to withstand those things. And talking about withstanding those things, let's talk about new attack trends. The interesting things which these guys have come up in the last 1 year. And this is an interesting one, carpet bombing. Basically, this means that if, for some reason, I don't like, for example, like you, sorry, I'm just using an example, then usually I would launch a huge DDoS attack against your services, your infrastructure or something. And let's say this is one service provider and you are one customer of that service provider. So usually I would launch one attack against your IP. But carpet bombing would mean I would attack everyone on this side of the room. And then when the edge service provider begins to deal with that, then I'll turn around and attack everyone on that side of the room. And then I would only attack the first 3 rows or whatever. I basically, instead of attacking one specific IP, I begin to attack the subnets, side the blocks, and rotate and do all those things. This is not new, but until now, well, until this year, this has only been done by people which have those skills, which have the understanding of how networking works, and they do it manually. But then this got weaponized, meaning it was now, this kind of attack type is now available for anyone on those attack toolkits, and they can use it to attack you guys. So let's talk about how this actually looks like. Carpet bombing, of course, they're just using the normal attack toolkits that is using UDP refraction, which means DNS, SSDP, NTP, and so on and so on. Attack size 10 to 600 gigs. They rotate the attacks within the CIDR blocks. Like, you have a 6/16, the attack is /20. And then after about 5 minutes, they rotate to a different one. And actually, this is still happening. And last Friday, when I was packing my bags to fly over here, then I was going to have a quiet evening, just pack the bags, look at TV, watch Netflix. And then, yeah, someone was being attacked in Brazil, and they were using exactly this technique. And the time from, that is, when we had managed to stop the initial attack, it took 5 minutes before they changed the attack pattern. New kind of attack against a different subnet. We stopped that one, and again, they changed. They actually did this 5 times, and it was a miserable Friday evening for me. But this is how they monitor what's happening, they look at what's happening, and they will change their attack patterns, rotate, new types, and so on and so on. And it can be challenging to stop. So, in addition, because these attacks are distributed across a subnet, then if you have detection mechanisms which are focused on measuring volume against a specific IP, then, because it's spread across the subnet, then maybe those things will not trigger. An example is like you have SSDP amplification, you set it at 4 megs. But you have a 40 gig attack distributed across 16,384 addresses. That translates into 2.42 megabits per TRS. But these 40 gigs, they are enough to fill the links to maybe stop all the traffic going through a specific box, and you do not know what's happening. We've had examples of service providers which are really good at what they're doing, but they didn't detect this, detect a multi-hundreds of gigs type of attack because of exactly this. Because they had tuned their detection systems to look at specific IPs, not at CIDR blocks. And to make life even more fun, then you will have a flood of IP non-initial fragments. And let me explain a little bit very quickly why these fragments are irritating. So if you have a UDP packet, let's say this is an NTP packet, then, well, okay, it's an UDP packet which is large, and this gets fragmented. The problem is, of course, when you have fragments, they do not contain the UDP header itself, which means you have no idea about which specific source port or destination port this is. It's just a fragment. Yes, if you reassemble it, of course, you will have the entire packet and could mitigate it, but reassembly requires resources. And if you're trying to deal with this on the network with as least resources as possible, then this can be irritating. If everything is within one packet, no fragments, you will always have the port numbers to relate to, or the length or something, which is not part of the non-initial fragments. So how do you detect these things? So, like I said, detecting volume against one specific destination IP is not good enough anymore. You need to start to look at volumes against specific network blocks, subnets, CIDR blocks, or whatever, or the volume of traffic going through interfaces. If that goes beyond the specific limit, then you need to start to look at it. Okay, it's not rocket science which I'm talking about, but the thing is, we have gotten used to detecting things in a specific way. We need to change that a little bit. Take a look at these new approaches such that we can detect this as quickly as possible. We don't want our customers to be our detection mechanisms. When the customer phones you and screams at you, that's too late, basically. Okay, but if you want to do things at list level, you will probably need to understand what's normal. What is actually normal? Is it normal to have 80% usage on a specific interface? And maybe that's perfectly okay. That's how your network is designed. Or we will solve that next month with this link upgrade or whatever. But if you don't know what's normal, then you have the risk of beginning to take action against something which you shouldn't be trying to stop. So profiling, measuring things, have some graphs on interface volumes, store them somewhere so you can take a look at them and see, okay, this is actually normal. I will not mess with this box. So mitigation, okay, this is a normal reflection type of attack. The only difference is the destination IP will vary a lot, which means you cannot put your filters in place against the specific /32 or /128. You could then potentially start to use the destination CIDR block, but the risk is when you have finally put everything in place and you now are mitigating attack against this /20, well, the guy goes to a different /20, and then you have to change it again. So what can you do? If you have information about the reflectors themselves, because of course they're using source address spoofing, pretending to be used, send it against an NTP server, SSDP server or something, and then this junk comes in your direction, then maybe you can use the reflectors IPs. And actually, I'll come back to it a little bit later on because we have a project which maybe will help you in this case. Then, okay, use the flow spec or source remote trigger black holing. One thing about those non-initial fragments, which are so irritating. We have been working with a number of customers, and some of our customers have come to us and said, this is what we do in a very successful way, is that if you have non-initial IP fragments, which are destined towards your network, and in most cases your access networks, then rate limit them down to low values like 1%. And this sounds interesting because usually you would not start to rate limit stuff because that's a big no-no in many cases. But we're talking about UDP fragments. And UDP fragments going towards your access networks, and your access network is usually where your consumers are, and those are usually the ones which are getting attacked these days due to gaming or whatever. And actually the 600 gig carpet bombing attack, but that was actually due to a gaming dispute. Someone didn't like the other guy, and instead of, well, in this case, he launched what I would call almost a nuclear missile against someone else, took out almost the entire network. But that's the issue. So and in most cases, in most cases, you would not have many UDP fragments going towards those access networks. So it's perfectly okay to rate limit those. And what we have seen from some of the customers we were working with, this has helped in blocking 1/3 to half of the attack just by doing this. The only thing you have to be careful of is that there are some fragments which are legitimate. And if you have traffic going towards your own DNS recursive infrastructure from the public DNS servers, don't rate limit that. Usually focus it on the access networks or against things you know shouldn't be receiving those huge fragments all the time. Of course, if you have intelligent DDoS mitigation boxes, you can just reroute the attack to those and they will take care of it. But again, don't take an entire /16 and mitigate it towards a cleaning cluster. I will probably kill it because that's too much. But if you move this /24s or /20s, you should probably be okay. But these are things you can do. So, new things, new twist in SSDP attacks. So this got a lot of attention earlier this year because there was a certain company out there which said, okay, there's a new way to launch SSDP attacks, and this will take down the internet. Well, it has actually been around since 2015, and the internet is still up, so it wasn't that really much of news. So my colleague, Matt Bing, he was actually presented during one of the lightning talks at NANOG 72, so I'll not go into too much detail. But basically, this resolves about there are SSDP implementations out there which have bugs, which means that instead of sending the replies back on UDP port 1900, they will send them back on a random source port. And based on our research, more than about 55% of those devices out there will send back the reply with a random source port, which is not nice, because that means if you have filters in place to block SSDP, they will no longer work. So how do you detect this? You can't use the source port anymore, because that is now random, and leaving you with a bunch of UDP packets, which you have to take care of, and potentially fragments. So, of course, using NetFlow, you will detect this. Then, how do you block this? Again, use FlowSpec, use the source IPs of the reflectors if you have those. You could potentially start to use some kind of payload inspection, because these things SSDP will either have UPnP 1/1.0 in the header, or HTTP 1/0 in the header as well. If you could then use those patterns to block, but that requires a regex, that requires maybe a device which you don't have in your network. Rate limit the fragments, or divert the traffic to cleaning clusters. So it's an irritation. It's just basically another thing to make life miserable for us. One interesting thing with this specific bug is that in some deployments, how do I say? This is lib UPnP on Linux, on small IoT boxes. And in some of those IoT boxes, they have an additional problem, is that this bug influences UPnP as well. And just to refresh your memory, UPnP is what runs on those boxes at home, which allow devices on inside to punch holes through the CPE, such that you can connect from the outside. Basically, a device on the inside tells your CPE, please open up some holes so I can connect to my device from the outside. That could be a webcam, could be something else. UPnP is evil. You should not use it. Block it, disable it, because it has all kinds of bugs. But in this specific case, the 1.65% of those SSDP devices we saw there, they allow someone on the outside to punch holes through the CPE device into your network. And that's taking user friendliness to extreme levels, I would say. It's good for the attackers, but this is the only thing you need. And this is exactly the commands we used. So basically, you create an XML schema. You specify the external port you want to open, in this case 2222. It's protocol TCP. The internal port should be 22. And the internal IP address should, like in this case, be 192.168.1.200. You send this to the CPE device, and the CPE device will say, OK, that's fine. I will now punch up a hole, allowing port traffic on TCP port 2222 to go through the device and to the internal device on port 22, which is SSH. And this actually works. Really nice and user-friendly. And we did a mapping of this, and this is basically, we detected 33,000 devices which had this specific bug, and this is the distribution around the world. So not that many, well, 613 in Canada, 1,250 in the US, a lot of them in Russia. Maybe that's a requirement by the authorities to allow the authorities to connect through your devices, but OK, I don't know. But I think it actually comes down to the issue that I was told in Russia, then the consumer will have to buy his own CPE device. And of course, what people, when you go into the store and want to buy a CP device to connect to the internet, you will always buy the cheapest one. Correct, it's cheap. And it gives me 100 megs or 1 gig or whatever. But usually the cheapest stuff has the most amount of bugs. So that's probably the reason. Okay, Memcached. There was actually a session on this on last NANOG, so we'll not go into too much detail, except that this is the reason why we got the 1.72 terabit attack. Memcached is this caching service, and the default implementation allowed anyone to connect to it on UDP and TCP port 11 through 11. And by default, it listened on all interfaces. This has been fixed now. So if you take the latest version of Memcached, deploy it, it will only listen on TCP and only listen on the loopback interface, which makes sense. But back in March, this was not the case. And actually, Artyom, he said that you could have a really crazy amplification factors. When I was testing this in my lab, I managed to get an amplification factor of 1 to 500,000. Meaning I sent one packet of 1,400 bytes. I got back a reply of 6.7 gigs. In real life, you will not get that because of all kinds of limitation interface speeds, but this is totally crazy. This is, I would say, the limits to this is basically the hardware itself and the interface links. So if you would have a powerful enough computer on a 100 gig link, it could probably fill that link just by sending one packet. If you need 200 gig attack, you send 2 packets, and so on, and so on, and so on, just for the fun of it. Okay, so what I wanted to add to this, I wanted to add a section on how to detect and mitigate. Memcached is simple. It is basically a UDP reflection, UDP packets, source port 11 to 11. You detect it easily, you block it, and you should basically be okay. One thing which is interesting about this basically has shown the attackers how easy it is to create a super powerful reflector. And what's stopping these guys to go into a data center, install a VM, spin up a server with vulnerable Memcached service, and then use it to launch attacks? Okay, maybe they'll get taken down in 1 or 2 hours, but that gives them, and if that data center operator has not done his due diligence regarding security, he can basically have a lot of fun for a few hours. So that's easy. One thing which could solve this is actually, this is a post which Job Snyder's made on the NANOG mailing list. And this shows what he is doing. And this is an excellent example. Put those things in place onto your network beforehand. If you know about bad things, put them in there, and this will save your day. It's a lot easier. Trying to do this during an attack is a bit bad. It is very difficult because everyone will be screaming at you, and your boxes will be collapsing, and so on and so on. But if you have it in place beforehand, then use it. Okay, one question. Memcached, and this question was actually raised earlier this year. Memcached has 2 interesting commands, one called flush and one called shutdown. Shutdown is simple, it basically takes down the Memcached server. Flush means flush the caching database and flush all keys. The way to get a big amplification attack is the attacker pre-position his own keys, really large ones, up to 1 meg, and then says, please get this specific key. Give me the value of that key, and then you'll get a 1 meg response. And if you ask for that repeatedly, like 722 times, which you can fit into 1 packet, then you'll get 722 times 1 gigabyte in 1 reply. Well, many packets, but yeah, that's how it works. The flush command means you should be able to then, if you issue the flush command, you will remove all the keys and clean out the database. So the question is, If you were under attack, someone is hitting you with a 1 or 2 terabit attack, and you can see it's coming from 100 specific sources which have vulnerable Memcached installations. Should you go and start issuing those flush commands or shutdown commands to stop the attack? Should you be fighting back? Should you try to stop the attackers? Who would do that if you're under attack? Please raise your hand. You're boring. The answer is, of course, no. Because these systems which are used to attack you are owned by someone else, and they are also a victim of this specific attack. The attacker himself, he's sitting somewhere in some country. Could be next to a neighbor, I don't know, but he's probably pretending to be someone else. But he's launching an attack, and he's abusing those servers to attack you. And in most areas of the world, it's actually illegal for you to go in and manipulate other people's systems. You're not allowed to do it. If you do it, you're as bad as the attacker himself. And this is basically stupid. If you're trying to fight back, you're doing a bad thing. And this, the reason why I brought this up is because people have been talking about this, well, I would say every second year this question comes. These IoT devices, should we be going out there and trying to shut them down? That is, those which have all kinds of bugs. Actually, someone tried to do that. This has been raised many other years back and so on. But basically the moral is, DDoS defenses are working pretty well. They're not perfect, but if you do your due diligence, if you harden your network and implement the right things, you will most probably be well off. If we begin to fight against the attackers, then basically what will the results be? It will be a virtual battleground, and basically everyone will suffer from it. So don't fight back, even if it is very tempting to basically do one telnet SSH, take them offline or whatever. So what I've been talking about now is basically, it's like we sit in a castle. And I like castles, you probably remember from last time. But the thing is, we have very little visibility. We sit there, and then suddenly there's this huge army outside our gates trying to come through. And when they arrive at our gates, we basically have to try to deal with whatever is happening at that point of time. We have no information about their capabilities, how they behave, why they're coming, and so on and so on. And also, these guys, they are really innovative. As soon as they come up with new kind of attack types, we try to deal with them, we try to educate everyone about this, and we will learn how to deal with, let's say, Memcached, or SSTP with random source port and so on. But then these guys will come up with something new. And then basically this cycle continues. New kind of attacks. Everyone says the world will collapse and so on, but we deal with it and so on. So they're constantly coming up with new stuff. And like, for example, Mirai, which came out in 2016. Since September 2016, there have actually been 5 new implementations of Mirai, which have new attack capabilities, new distribution mechanisms, and basically becoming more and more clever and intelligent. So what I'm trying to say is that we need to try to become more clever in dealing with this. So seeing through the fog. One thing which could be interesting is to try to detect those attacks and how they look like in real time, preferably before they happen, but at least when we see that they are happening, then we can know what the capabilities are. Like, okay, we know the Viking army is on its way towards us. And we know the Vikings, they have these kind of weapons and so on and so on. But no, okay, tomorrow it's the French who are coming to attack the English or something. And they have siege weapons. They are able to break down our doors. So we need to strengthen them and so on. And this is actually something which we began doing earlier this year, is that we have infiltrated those botnets. We pretend to be vulnerable IoT devices, and we allow them to infiltrate us. They think they're injecting malicious software into our devices, but we just we accept it, and then we say, okay, we are here. And the example on the right-hand side is actually one of our pretend IoT devices received an attack command to launch an UDP attack against someone in the US on port 3074. The example at the top shows you we pretend to be reflectors. So in this case, we are pretending to be an NTP reflector, meaning someone scans the internet, has found us, and is now trying to use us to launch an attack against someone else. So this information can help our customers to say, hey, well, you are going to be someone is sending out attack commands against you using these protocols, and they're using this malware family. That means these are their capabilities. It will help you to fight against these guys. Also, what we are starting to do now is we are going to be scanning for those reflectors and building lists of known reflectors which have been abused in the past. Meaning, and this is something which we are going to be sharing with you guys, such that you know, here's a list of bad things which are currently being abused by the bad guys, which can help you if you're facing an attack. Okay, like I said, we pretend to be IoT devices. We accept the malware, which is good because then you can reverse engineer it. And we implement things like DNS sinkholes, such that we can find out where there are vulnerable devices, and so on and so on. This all creates information about the attackers, the capabilities, where the devices are, and can then hopefully help us to build better defenses and help you guys when you're facing an attack. So that you know you're being attacked by the Vikings or you're being attacked by the French army or whatever. Then you can tune your defenses to who is coming there. So, summarizing, we're into the terabit era. We have now attacks going beyond 1.7 terabits. They're harder hitting. You need to follow the security best practices because these guys are constantly adapting to whatever you're doing. So scan your own networks, block rate limit things, like what Job Snyder was explaining. Use those things, they are really good to help you to defend beforehand, before you get attacked. And also make extremely strict requirements of your vendors. The reason why I put this up is that earlier this year, we had a service provider in a certain country in Southern Europe calling us because the entire access network was down. The reason for that is that they had recently purchased around 10,000 new CPE devices and deployed them to their customers. Those CPE devices had a specific vulnerability. And someone had scanned the network and was now using those 10,000 CPEs to launch outbound DDoS attacks, basically taking down their entire customer network due to this. Yes, if they had installed the latest patches, then it would have been okay, but in this case, their network was being used against them, or basically they were using the network to attack someone else, and yes, they had a bad day. So the solution in that case, they blocked the CNC communication and then had to go out there and replace all those 10,000 devices, which was a lot of fun. And soon, we'll be making this new information sources available to help you, because we need to become better at this. We cannot just sit there and accept all the crap coming in our direction. So, thank you for your attention. And if there are questions, then please bring them on. Thanks.
Hi, Jared Motch from Akamai. So I have a curious question for you. So I've been tracking kind of the DDoS trend line for a number of years of just kind of figuring out where it seems to be compounding itself. And it seems to be compounding itself at around 150% per year. So if we're at 1.7 terabits for 2018, my projections kind of say that we're going to be up there. Have you been doing similar trending and kind of followed that? Because I've been following this since the first, 100 gig attack, and I reverse calculated with all the big ones that hit the media, all the way back to, with the exception of like probably the original carpet bomb attack was SQL Slammer back in 2003, where everything was just full.
Yeah. So I tried to do that, but I've stopped it because these guys, they exceed everything I can ever imagine. So it'll continue. It'll continue. There will continue to be software vulnerabilities, and they will be used against us. And maybe the volume, one thing, taking one step back, maybe the volume might start to go down because the attacks are so effective, they can do all kinds of things. But as we get better defenses, they will just change the tactics and become more clever. So will it go up? Will it go down? No idea. Will we continue to get hit and have problems? Yes.
Okay.
Good afternoon, Don F5. As attacks get larger, as potentially multinational corporations either become targets or part of it, do you see cases where it becomes acceptable to hit back?
The problem is hitting back. Who should you hit back at? The number one rule is the attacker will pretend to be someone else.